Hey guys, so this is the first video for the chapter 18 notes. I will make a part 2 when we get to that section, but right now we're going to talk about 18.1, and at the end of these slides there's a little bit on 18.5 just because the topics kind of overlap a little bit. But this is the first chapter 18 video, and once you watch this video, we'll be getting, and take notes on it, we'll be getting into that new packet, the one that I gave you in person right before this break happened. So that's that really thick chapter 18 packet that you did 2 pages in already, but the rest of this packet corresponds to what I'm going to start talking about today. So after this, in a few days, I will post some instructions for doing some more pages in that packet. So what we're going to be talking in this chapter is about how reactions happen. So spontaneous reactions, non-spontaneous reactions, how that kind of happens, how we can make reactions occur faster, how we can make reactions happen at all, and what we call the collision theory, which is basically how and why reactions are able to occur. So first we want to introduce, rate and how we mean rate in chemistry, because how we define rate in chemistry is different how we would use it in physics and physical science, and biology is different as well. But in chemistry, the rate of a chemical reaction is called the reaction rate. So this is an important term. So reaction rate, and it's usually expressed as like reactant changing per time. And so what that means, it's going to be like millimole per second. So what that means is how many millimoles of new product substance is created every second. And so I'll kind of get into more of what that means. And if you haven't already, make sure you either open up these notes in the agenda or Google Classroom, wherever you want to open it. I did download it as a PDF because I want you guys to be able to use Kami, that program I put a tutorial of on Google Classroom, if you want to use Kami. Otherwise, you can just print out the PDF of these student notes, or you can write them, on a separate piece of paper and just put them in your binder. Okay? But so the first thing we're introducing here is just reaction rate of a chemical reaction. And so, like I said, a rate is just kind of, in chemistry, it's going to be millimoles per second. That's our unit. And it's just, how much reactant is changing into the product per unit time. But in general, a rate is just, the measure of the speed of any change within an interval of time. So an example of that, so this is more of a physics example right here. Someone running, this is definitely a physics example. But in physics, you have the unit meters per second. I'm sure you've heard that. Technically, miles per hour is also a rate. So when you're driving your car and you go 20 miles per hour in a school zone like you're supposed to, that is a rate. You're going 20 miles for every hour. Meters per second is so say you're running and you do like 5 meters for every second. I feel like that's really fast, so I feel like that's not practical, but like a cheetah or something. But in chemistry, we use the millimole per second. We use how much reactant is being changed into a product per second. And so what we mean by like reactant turning into a product per second, this is kind of a good visual to help us see how that's measured and happening. So we have this at time 0. We assume this is time 0 because the clock hands are pointing up. We assume that, this is the start of the reaction and nothing has happened yet. So at time 0, nothing's happening. But as we progress on the time, we're going to see how much reactant is changed into product. So we see, after a time, a little bit has, then a little more, then a little more, and finally almost all of it. And so that rate that happened at is, specific, and it will be given a value, like I said, in millimoles per second. And so the rates of chemical reactions that's just how they're measured. They're measured of how much reactant is converted into product per second. So let's just say all this happens in the span of a second, okay? And let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 millimoles were converted from reactant to product in that second. Okay, so that's just an example of what a reaction rate for this fake kind of example reaction would be. And so now we're getting into this thing called collision theory. And this is just kind of how, reactions actually happen. They happen by collision. And so in collision theory, the things that are reacting, so in our case, it's going to be like an atom, an ion, or a molecule. Those are going to be your reactants, right? So, you can have like a combustion reaction where you're reacting with like oxygen, and one of your products can be like CO2 or something, depending on what you're reacting with. But so you can have, atoms as your reactants. You can have ions. You can have molecules as reactants. And when they react together, they're going to collide with one another. That's why this is called collision theory, because we have collisions. And if these collisions are energetic enough and strong enough, they'll knock into it and create something new, like spontaneously. So we see in this reaction down here, we're going to assume this is H2. So this will be like H2. And this will be O2, like water. It's going to create water. And so, in our collision theory, we're going to say that in this jar we have hydrogen gas, which is H2, and O2 gas. And they're like, vibrating because, it's like energy and flying around so fast, and they're going to hit each other hard enough in this little glass to start making and reacting to form water. And so we know that, where's my cursor? We know that there's enough kinetic energy because that's a requirement in order to have a successful reaction. So in order to have a successful reaction, we need to have enough kinetic energy with, like, in the particles in order for them to like hit each other enough and completely make, something new. So these things are all going to collide, and out is going to pop water. And later, when we get to something called transition state, I'm just going to tell you right now, this would be your transition state. So just so when I'm talking later and I say the word transition state and you have to write the definition for it, you have an idea of what I'm talking about. So it's just the transition from, these two molecules to create these molecules, which are different. Okay? But the basis of collision theory is just that you have, your reactants, which can be atoms, ions, or molecules. In this case, they're molecules. And they, can react to form products, but they have to have enough energy when they collide to, make something new. And so this, if you look, is called an effective collision because we had enough energy and we made something new. But here, this would be an example of an ineffective collision. And remember, ineffective means like it doesn't work. So in this ineffective collision, we have, our O2 and our H2s. And when they, bump into each other, they don't have enough energy. Or the orientation of the molecules is not right. So, like, do you see how they're hitting head on here? Versus in this, they're hitting, like, sideways. Sometimes that is a factor as well. And so it's just based on how they collide and if they have enough energy when they do collide. So we're going to say that these, O2 and H2 molecules did not have enough energy and the orientation was wrong. And that's why this did not work. And so because of that, when they collide, they just kind of bounce back and they don't really do anything. So they bounce back the same as they were when they bounced in. So this is still O2 and these are still H2. So those are still, H2 and the red is still O2. So nothing changed. Everything's the same because it's ineffective. And so since it's ineffective, no reaction occurs. So in collision theory, we have what we call the activation energy. And what the activation energy is, it's the minimum energy that the particles that are reacting, so it's the reactant particles, the minimum energy that they must have. So for this example, what this is telling you, this chart here, and this chart is going to be very important in the future. I'm going to move my head there. So this is going to be very important in the future. But so we have, these reactants, and, they might be colliding, but they don't have as much energy. But when you get to this amount of energy, yes, you do have enough energy because this is your activation energy, and this is the minimum energy that you need. Okay, so if you reach this energy, you have enough energy to convert your reactants to products. And so that's what's happening here. So your activated complex is when you have enough energy, your collision was successful, and then once this happens and your energy, you collide and your energy is enough, then the energy is going to go down because you created the new product, and that's what you wanted to do. Okay, so that's what this whole chart is telling you. It's telling you that once you have enough energy to make that product, then the energy is going to go down because it's what you want. But you have to get over that initial hump of energy. It's like when you're, say you're not a morning person. I am not a morning person. And so say you're sitting in your bed in the morning and you're like, I do not want to get up, and you have no energy and you're so tired. It just takes a little burst of energy to be like, okay, I'm just going to get up. I'm just going to do it. And so it takes a little, burst of energy. And that's what's happening here. To just get out of bed and just do it, rip the Band-Aid off. And then, once you're out of bed and you have that burst of energy, you can rope around the house again. You can slug around the house and just kind of ugh, I can't believe I got up that early or whatever. But you did do it. You got the energy and the strength to get up. But then, you're walking around your house again, really slow and tired. But at least you got up. And so that's kind of how I think about this is you just need the energy to react. And then once you do, you're like, okay, now I have what I want. Now I'm good. So I can lower my energy now. And so, our activation complex, so this is where you're going to have your reaction occurring. So I'm going to make a little note and say reaction occurring. And this is when you're at your peak. So I think it actually says this. Yeah, it does. So when you're at the peak of the activation energy, so once you, get enough energy and actually do the reaction, this is when your reaction is actually occurring. And it's kind of an unstable arrangement. And we know when something is unstable, this means that there's a lot of energy. So when we say unstable, we know there's more energy. So there's more energy in unstable things than there are in stable things. Because when you're stable, you're happy, you don't have a lot of energy, you're good. But when you're unstable, you're like, oh my God, I gotta change, I can't be like this. You know what I mean? So unstable arrangements of atoms are highly, highly energetic. And that's when your reaction's occurring. And then that's why you have that dip afterwards, because you're more of a stable arrangement, and so you don't need to have all that energy that you did when you're unstable. And then finally, you can't really see this down here because of this, but so your activated complex is called your transition state. And I kind of said that, where are we going? Right here. So this is where your transition state is. So in this graph where it goes like this, oh my gosh, come on. It goes like this. This is going to be right here. Okay, so you got over the activation energy and you're at your activation. So we can go back to this, and I already said reactions occurring, but you can also put here like transition state. So that's actually what's happening there. And so, how fast a reaction is going to occur, so the rate of the chemical reaction depends on the temperature of the, what's being reacted, the concentration, so how much of the things are in there. So if you only have I guess I'll explain these when I get to them. Particle size, so how big your particles are. If you have small particles, they're not going to collide that often. And then if you use a catalyst. So I don't know how much you've talked about catalysts this far in chemistry. You should have touched on them a little bit in biology, because they are a big topic in biology. But catalysts help you get the reaction done. And so if you use a catalyst, that will affect your chemical reaction rate. And so here's an example of each. So, oh my gosh. So I've said this before. Temperature is a measure of how much kinetic energy something has. So if you have low kinetic energy, that usually means your temperature is going to be low as well. Okay, so if you have something that's like ice, remember ice, the particles are just vibrating. And that's why you have such a low temperature reading, because if you have very small vibrations, that's not much energy. And so when you measure the temperature of those ice cubes, it's going to be really low because there's very little energy. Versus when you have a gas and you measure the energy of a gas, because we know gases are all over the place, they're moving really fast, they have a lot more energy. And so if you measure the temperature of a gas, it's going to be a lot higher of a temperature, a lot higher kinetic energy than something like the ice, which has very little energy. And so for that reason, temperature is vital in reaction rates, because if you have something that's moving really slow, like these little particles, they have no energy, right? And so it's very hard for them to collide enough for something will actually happen. So nothing's really going to happen if it's cold, or it's going to happen very, very slowly. Versus when something's high and all the particles have a ton of energy and they're bumping into each other and they all have this energy. Do you like my I don't know what I'm doing. But when they have a ton of energy and they're really hot and the temperature is, reading is high because of all this kinetic energy, that's when you're going to have your reactions that are faster, okay? So, when you put food in a refrigerator, the reason you do that is because you don't want your food to spoil. And what food spoiling is bacteria eating your food. And the reason why you can't eat rotten food is because you don't want that nasty bacteria inside of you. You could, potentially get sick from it. And so we put the food in the fridge so that it has a low temperature and the kinetic energy of the particles and everything gets really low. Okay, so there's not enough kinetic energy. We basically halt those chemical reactions that the bacteria are trying to do by decomposing our food, because the bacteria need a certain temperature to be able to do that. But when we put it in the fridge, it's too cold for the bacteria to do that reaction, because remember, low temperature, low kinetic energy. So that's why we put food in the fridge, to slow the rotting down. So when we have, this is an example of temperature. When we have an example of concentration, remember, concentration is how much stuff you have in, a certain amount of space. So say you have and this will be the example that I'm about to show you. But say you have this is talking about oxygen. So say you have, this is the normal air where you have where you have some oxygen. You have a few. And so the fire can ignite because, for fire to happen, you need oxygen. So we have some oxygen here for fire to happen. And so because there's not that much, but there's still some, but there's still some. So we will get like a little reaction. So we have a little fire here because we have like just enough basically. But if we have a really high concentration, so that's like a lot of stuff, there's a lot more to react with. Sorry, these are my O2 molecules. They're kind of ugly, but I'm sorry. But so when we have more oxygen, there's more stuff to react with, right? And so because of that, we're going to burst into flames when we have a fire, okay? So this is just saying like, you do have a fire, but, it doesn't last long and it's very small, as you can see. But then when you have, straight oxygen, which is a very high concentration, so this is high concentration, and this would be like a low concentration, you're going to have more reaction because there's more stuff to bounce into. So if you think about it on a molecular basis, remember I told you collision theory and reactions actually occurring is all about like how much stuff bumps into each other and, how fast that happens and if they have enough energy, right? And so, maybe there's like one or two oxygen molecules out there to combust this splint. And so, it's going to hit the splint every so often. And so it's going to be dull and eventually go out. But if you have your splint and you have a ton of oxygen there, more collisions are going to occur like this. I hope these visuals make sense. But, more collisions are going to occur because you have more oxygen molecules. And so that's how concentration will affect your reaction rate. So the next thing that we can talk about in terms of affecting the reaction rate is particle size. So how big of particles we're working with and how big of particles that we actually have to change. So if you have something small, then it's easier to kind of change it because you're not changing much, right? Think about our previous example of our, little H2 combining with our bigger O2 and reacting to form waters after they've collided. Those are pretty small particles. They're just, molecules made up of two atoms, right? They're so small, in fact, all those gases are floating around me right now and I can't see them. We're breathing in oxygen as we speak. And so those are pretty small. So those reactions are happening pretty easily because the particle sizes are tiny enough where it's easy to make that, quick change. When you have something that's bigger, think of like, two football players on the, and I mean football as in like American football, not like soccer. When we have, American football and we watch two people and someone gets like sacked, I think that's the right word, but two football players like hit each other. I mean, did any reaction happen? I mean, they might have, bounced back from each other and fell backwards or something, but no one changed. Like there was no reaction that happened. And it's because we are made up of so many particles and there's just too much to change. And plus, you'd have to have a lot more energy than just, running at yourself, like each other. But so the easier it is to react depends on, the smaller particle size. And so because of this, we have this example that says the minute size of the reactant particles in this kind of explosion here that's depicted. So we have grains of dust, which are really tiny. And then the mixture of the grain dust with oxygen in the air, which we already know from up here is tiny, cause the reaction to be very explosive. And so what that means is the reaction happened really fast because explosions occur really quickly. And, it was easier than if we had like bigger dust. So that's how particle size affects your reaction rate. So smaller particles are just easier. And so finally, we have what's called the catalyst. I'm going to move my head. So we have the catalyst. And if you remember from biology, catalysts help reactions occur. Okay? So biological catalysts, when we talk about biology and catalysts, they help, things occur. Like in our digestive system, catalysts help us break down food more easily. And then in chemistry, we can think about, I already showed you this graph, but what happens is catalysts lower the activation energy. So I'm going to put lower activation energy, because that's what catalysts do. And so we can see the original reaction is here in blue. And so you've seen this because I've showed this to you. So you have this reaction here in blue, and it goes up because this is the original activation energy, and then goes back down when the products are formed. But when we have say it's really, really hard to get this much energy, like it's really difficult. And so the reaction takes forever and, is really slow. But if we use a catalyst, the reaction, the activation energy gets decreased. And so we have lower activation energy. So our particles don't have to be that much higher in energy than they were here. And so it's just easier to complete the reaction faster if we do use a catalyst. And so we have different kinds of reactions. So we have an elementary reaction, which is just one step in the reaction in a transition state. So we have our transition states that I showed you earlier. So when we have an elementary reaction, this would be an elementary reaction, just like the first step, okay? And then you'd have your intermediate. And then you'd have, another elementary reaction, and then have another intermediate. And, it keeps going until you finally have your product. And so when we have all of those elementary reactions, so, we have like several. So in this example, we have 1, 2, 3, 4 elementary reactions. But together, all those elementary reactions are the reaction mechanism. The reaction mechanism is just, all of the elementary reactions or steps that take place in this complex reaction. So in this example, we have these 4 elementary reactions, and then together those 4 elementary reactions make up the reaction mechanism. And so finally, we have intermediate. And this is just like the product of one of those little reactions that we have within the big complex reaction. So what that looks like is, so I told you we have these 4 elementary reactions, and then in between each, this is like the product, the baby product of, each of those individual reactions. But we know that that's not actually what we want, and that's why we have so many individual reactions, because, this isn't our final product. It's just, an intermediate product. So it's just in between the steps. And so that's what all these valleys are. All these valleys are going to be our intermediates. And then, after this final elementary reaction, we have the product that we actually want, not any of these intermediates that we don't want. And I'm just going to note at each activation complex, we have, so this is our activation complex. And then these are also our transition states. So I'm going to note that intermediates are not the same as transition states, okay? Transition states are, the middle of the reaction that's actually taking place. And then the intermediates are what's happening after this single reaction takes place. And this is, like I said, it's kind of like the intermediate product. It's like the product for now until we get enough energy to do this reaction. And then here we have our transition state again to get the intermediate product. And then we're waiting around until we have enough energy for the next final elementary reaction, until we finally make the actual product that we want. Okay, so intermediates are not the same as transition states. Transition states happen at the peak, and intermediates are like the baby products that, they have lower energy. And the difference is that intermediates have low energy and transition states have very high energy. Remember, transition states are unstable, but intermediates are, kind of stable. They're not what we want. What we want is down here at this actual product, but, they have littler energy than transition states. And so the intermediate, like I said, is just the product of one of those steps. Okay, so I'm going to put, because I keep saying this, it's, like the kind of product. and you don't have to write this, but it's just if I refer to it like this, you can say, like, it's like a product, but like kind of, because it's not what we want, but it is like more stable than what we had up here. And so this is just a reaction progress curve, and I've already shown you one here, and I've shown you one here. So these are both reaction progress curves. And so what these show you is like if you have enough energy here, and then you get this intermediate, and then you have to have this much. And so say you're like here, this is where you are in the progress of this reaction. And so that's all this tells you. But remember, each peak is a elementary reaction. Each valley is a intermediate. And then finally, the product is over here. Something I want to note really quick, which I don't know if you guys picked up on this, but usually our reactants have more energy than our products do. So I'm going to say more energy than products. Just so you know, can note that and kind of see how we have a higher energy here with the reactants, and we're closer to being able to get to this activation energy, complete the reaction, and then finish. And then the products usually have lower energy. And so I kind of already said this, the peaks correspond to the elementary reactions, and it's already noted in this last one, but these are also activation complexes. And this is where our transition states are. But so each peak is an activated complex. It's the activation energy we need to reach. Because remember, we have to have enough energy for the reaction to happen. And so that's why we have those peaks. And then each valley is an intermediate. And like I said, those have less energy than the transition states in the activated complex. If anything is not clear, please let me know and I will clarify. And so now we get to the little section quiz at the end. So our first question is asking the units below that would be appropriate to measure the rate of reaction is. And so I already told you that moles are involved. And so we know that rates are per unit time. So they're per unit time. And we only see one unit of time here, and that's going to be seconds. Like we don't see any seconds here or here. We don't see seconds here or here. And we don't see seconds here or here. So that actually, makes it easier for us because it leaves just this first one as our answer. Because I told you in the beginning it would be millimoles per second. But if you look at this, and even if I didn't tell you that and you weren't sure, and I told you that rate was a reaction, rate was a measure of per unit time, you could still figure that out because we only have seconds in this first answer. And so that's our correct answer because it's per seconds, because it has to be per unit time. In a chemical reaction, the energy of reactants is always, and so I literally just said this, so when we look at one of those charts, it's, in a normal spontaneous reaction that happens like by itself, it's going to be like this. And so if this is energy going up like this, we know that energy of the reactants is higher and the energy of the products is lower. So let's find an answer to match that. So the reactants is always greater than the energy of the products. Yes. More than the activation. No. Less than the activation energy. Yes. Less than the energy of the products. No. So we have to say that, so in a chemical reaction, the energy of the reactants is always going to be, less than the activation energy. Because in our cases, we could say the product energy is less than the reactant energy, but that will not always be the case. Spoiler alert for the next video. But so we have to say it's less than the activation energy because the products are always going to be here and the activation energy is always going to be up here. In this case, the activation energy is always going to be higher, but here we have the energy of the products being less than the energy of these reactants. Sometimes it's reverse. Like I said, spoiler. So an increase in which of the following will not increase the reaction rate. So I went through these one by one. We talked about temperature and putting things in the fridge, so we know that's for sure. If we increase temperature, that will for sure increase the reaction rate. If we increase the concentration, that's more things to hit each other, more chance of a reaction to actually occur. Surface area of reactants, that means when you have a smaller particle, you have smaller surface area. And so what did I say about smaller particles? It's easier to change. And so your reaction will happen if you have smaller particles. But what I did not talk about was mass. Mass has really not much to do with it. So mass is definitely not. And that is correct. Because temperature, an increase in temperature, an increase in concentration, an increase of the surface area, which means getting smaller, will all increase the reaction rate. Final question. So a catalyst works because it either A, lowers the activation energy, B, increases the temperature, C, is permanently changed in the reaction, or D, supplies energy to the reaction. Well, I can tell you, we didn't say anything about increasing the temperature, so we know it's not this. I will tell you, catalysts do not change at all. Catalysts always remain the same in a chemical reaction, so they are never changed. They help other things change, but the catalysts themselves do not change. Do they either supply energy to the reaction or do they lower the activation energy? Spoiler alert, they do not supply energy to the reaction. They don't give you any energy. They just lower the activation energy. So if we click, we know that is the correct answer. And so catalysts lower the activation energy. They don't do any of the other things. Okay? If you have any questions, let me know. I want to know if you're confused, and I want to help you clarify those so these notes make sense, because in a few days we will be working on papers that have to do with these notes, okay? Hopefully this made sense. Hopefully you took some good notes on it, and we will, get a little more into chapter 18, a little more into this week.